Yes?
Can you remind us to what extent we're supposed to believe the formula for delta? Like there could be a constant multiple or a function of b multiplying?
Oh, yeah, well, there is a function of b multiplying it, but that's a definite function of b. I'm just not writing it. So there's the powers of b over the ADS length. Those come from a proper solution of the Poisson equation, which I just wrote as an exponential.
Yeah, but we care that g is there, but we don't care what's multiplying.
We care that, oh, did you say b or g? Oh, yeah, so this formula has, the iconal phase has corrections at higher order in g Newton, let's say in gravity in 4 dimensions. And those have been studied to some extent. And they make very little impact on the out-of-time order correlator. So they totally change the picture for scattering at high energies, but the out-of-time order correlator ends up not being sensitive to those energies. It ends up being sensitive to energies where this formula is a good approximation. It's, yeah, yes?
Douglas, I have a question that's bothering me about this idea of quantum chaos. If I thought the classical system is defined to be chaotic if there are Lyapunov exponents, positive Lyapunov exponents. If I have a quantum system which has a spatial locality, and let's say it's not a large n system, then it doesn't have a quantum Lyapunov exponent.
Yeah. Yeah.
But you wouldn't, I don't think you would want to say it can't be quantum chaotic.
No.
So quantum chaotic is not defined by this.
Absolutely, not by the exponential behavior, no, no.
So I think it's a little bit misleading, perhaps, to call it a Lyapunov exponent for that reason.
Oh, maybe, yeah, maybe so. Yeah, we could use another name, like call it chaos exponent or large n chaos exponent or large n many-body chaos exponent or something. But actually, I don't know a really good definition for chaos in the. So Lenny was asking about a system in finite volume without large n. This is something that we've talked about a few times. And the working definition of chaos that we used was that all of the out-of-time order, pretty much all of the out-of-time order correlators should go to 0. That definition didn't involve any exponential behavior. But I don't know whether that's a good definition or not. It might be that, yeah.
There's a sort of standard definition that if the system has a classical analog, if the classical system is chaotic.
Yeah, but that definition won't. So Lenny said that there's another definition for systems that have a classical limit, where you could just define it as chaotic if the classical limit is chaotic.
A bunch of spatially ordered anharmonic coupled harmonic oscillators. Coupled anharmonic oscillators, I think people would say is quantum chaotic.
Yes.
But it would not have the Lyapunov exponent.
No, it would not. But it probably would have the feature that all of the out-of-time order correlators would go to 0. So there wouldn't be exponential behavior, but you would have the butterfly effect. Yeah. Okay, so now it's time to start properly. Let me start by commenting on a question that came up after the lecture yesterday, which has to do with another derivation of this iconal phase, which we described using a Tufts sort of shockwave picture. There's another derivation, which I mentioned briefly in the lecture yesterday, and there's a third, even sort of more systematic derivation, where you look at Feynman diagrams for the scattering process, graviton exchanges, and in the high energy kinematics we're considering, you can simplify this propagator a little bit and simplify the vertices, and that allows you to do the sum over an infinite set of crossed ladders, and that sum gives this iconal phase. And this is a nice way of deriving the expression. Now, something that seems sort of potentially confusing about this is that in our discussion of the weakly coupled theory, we also computed ladder diagrams. But the interpretation of those ladder diagrams is very different. So in particular there, to compute the order 1 over n squared e to the lambda lt term, we had to sum an infinite set of ladder diagrams. These ladder diagrams here. Whereas in gravity, we get the corresponding behavior, g Newton times s. This becomes 1 over n squared e to the lambda lt. just from the exchange of a single graviton. So morally, we can think of the graviton in the bulk theory as being sort of like an infinite series of ladder diagrams, but at strong coupling. And this iconal exponentiated gravity amplitude corresponding to many graviton exchanges would be something that hasn't been computed really, at least by this method, in the weak coupling case, but would involve something like many ladders, exchanges of multiple ladders. Yeah.
What? You have infinite ladders, and then you also have infinite ladders?
Yes.
What's the difference exactly?
Another ladder, by another ladder, I don't mean adding rungs to this ladder. I mean a diagram that's a little bit hard to draw, but maybe it would look something like this.
Thank you.
Where we have another ladder over here, and it has its own set of rungs. I don't know if this is exactly right, but something like that. Okay, so now let's pick up where we left off in the lecture yesterday. We had this formula for the out-of-time order correlator as an integral over this data, these wave functions, with this iconal phase, which we computed in gravity to have this expression. So let's now plug that in and try to analyze the consequences for the out-of-time order correlator. Let's imagine first that we expand in powers of g Newton. So at order g Newton to the 0, e to the I delta is just 1, and we have an integral, a factorized integral over just the products of the wave functions. And that gives us a factorized expression, which is just the product of 2-point functions of the w and v operators. So that would be at order g Newton to the 0, just get the product of 2-point functions. But now we can expand down to linear order in g Newton. And so we'll expand that down, and we get a term like 1 plus I times g Newton times the typical value of the Mandelstam S parameter in the ensemble described by these wave functions, which we've argued is e to the 2 pi over beta times t. And then the typical value of this function here, which, at least if the operators are fairly well separated, will be of order e to the minus mu times just the separation of the operators in the y direction, in the transverse direction. And then we'll have higher orders in g Newton. So if g Newton is small, then this is a small correction, but it's growing exponentially in time. So we should identify the growth exponent here as the Lyapunov exponent or chaos exponent or whatever. And it has this particular value, 2 pi over beta. Now the coefficient here is imaginary, but if we look at higher orders, we'll find real coefficients which tend to make this out-of-time order correlator decrease. And that's very plausible because if the time is large, we'll have very large values of the Mandelstam S parameter, and we'll be integrating these wave functions with some kind of rapidly oscillating phase which will tend to suppress the integral. Or more physically, we're computing a scattering amplitude of these in and out states, and the effect of the scattering is to translate the states in this null direction. And the states, if the translation is large enough, which will be true for large time, the states will have very little overlap with their translated selves. So the overlap will go to 0, and this out-of-time order correlator will become small. For a general black hole background, it's difficult to compute the actual function that you get here, because the wave functions would require, knowing the wave functions would require knowing the bulk to boundary propagator in the black hole background, which in general is a difficult to solve wave equation. There are some examples where you can compute the wave functions exactly, like in ADS3 or ADS2. And especially in ADS2, you can actually do the whole integral. And you get an expression involving hypergeometric U function. But the behavior, let's say, of the real part, or the absolute value, doesn't matter too much. Looks something like this, where in this region we have 1 plus a very small but exponentially growing correction, or 1 minus a very small but exponentially growing correction. That's characterized by the Lyapunov exponent. And in this region, at late time, we have exponential decay, which is characterized by the quasi-normal modes. So this is a sketch of OTO of t as a function of time. And the time where this function really starts to decrease is this time here, t star. It's a function of the separation of the operators. And it's just the time when this first correction becomes of order 1. It's approximately at that time when the function really starts to decrease. Now, as we discussed yesterday, in the boundary theory, G Newton is related to 1 over n squared, 1 divided by the number of degrees of freedom at a point. So we can write a formula for the time when this out-of-time order correlator starts to become small, just by setting this expression equal to 1, beta over 2 pi times log of 1 over G Newton, or log of n squared, plus beta mu over 2 pi times y. And this combination here is sometimes called 1 over VB, the butterfly velocity, for reasons that, well, you can probably guess. So this formula combines aspects of both the k-locality of this theory within a given site, reflects the k-local but non-local interaction of the matrices, and also the ballistic motion as a function of space, which we discussed in the context of the Lieb-Robinson bound. So we can draw a type of space-time picture of this function, where this is time, and this is the separation of the operators, y. And let's draw the region where this out-of-time order correlator is small. That's the same as the region where the commutators will be large, will be of order 1, squares of the commutators. It's everywhere inside this, this point, where the separation in time here is what's sometimes called the scrambling time, beta over 2 pi times log of n squared. That's this separation. And the slope of this curve here, which is like the speed of the emergent light cone, is 1 over VB. So for example, for the black brane in d space-time dimensions, VB is square root of d minus 1 over 2 times d minus 2. And it's less than or equal to 1, and equal to 1 when d is equal to 3. N squared is the...
Is this super Yang mill?
Yeah, we're discussing that case.
So it would be n in... it's the number of independent components.
Yeah, it's the number of degrees of freedom per unit volume. Yeah. So the true light cone is somewhere like this. It's a faster slope, shallower slope, and then this one. And this one is offset by time beta over 2 pi log n squared. Now, one point that's sometimes confusing that I want to clear up is the following. This emergent light cone that we see here is not based on some kind of causal propagation or light cone in the bulk. It arises because of a competition between exponential growth in time and exponential decay in space that you can see in that function there. So it's not associated to bulk causality, it's associated to that competition between factors, which is the same place that one finds the emergent light cone speed coming from in the Lieb-Robinson bound. Okay, so next, let's take a tiny step back and try to understand where in the bulk theory this particular exponent 2 pi over beta came from. So that came from the property of the dependence on Mandelstam S of this iconal phase factor. And if we work at tree level, just at order g Newton, then we can think about it as follows. We have a scattering problem where we're exchanging a graviton. Our P and our V and W operators have momenta P and Q. Let's say we're exchanging a graviton with some transverse momentum K. Then, well, if we Fourier transform this phase factor from impact parameter space to transverse momentum space K, then this looks like an expression that's g Newton times S over k squared plus mu squared. Then Fourier transforming this expression back would give us the exponential decay in B. Now, if we consider a more general field exchanged here with spin j, then the generalization of this formula that we would find is s to the power j plus 1, to j minus 1, divided by, again, some kind of massive propagator in the transverse space. It's massive because we're studying this on a black hole background. The mass squared is a curvature effect. So in particular, if we consider exchange of bulk scalars or gauge fields with spin 0 or 1, then we won't find growth as a function of s, and we won't find this exponential behavior in time. So we got this particular exponent, 2 pi over beta, because the spin of the graviton is 2, and that determines the rate of growth of this amplitude. Now, in the n equals 4 super Yang-Mills theory, at finite de 't Hooft coupling, the bulk theory is a string theory. And in string theory, we have fields of all spin. And a consequence of that is that the behavior, even just of the tree level amplitude, at high energies is non-trivial. It's an interesting function of S. And, well, in the kinematics that's relevant here, which is, it's called the Regge limit of fixed S and, of large S with fixed transverse momentum. String theory amplitudes behave formally as though you were exchanging a field of some fractional spin. Or what that means is just that the power of S corresponds to j minus 1 with j a fractional value. So for example, in flat space, if we consider small transverse momentum, then flat space, so the Virasoro-Shapiro amplitude, we get s to the power 1 minus alpha prime k squared over k squared. So the growth with s is a little bit slower than in gravity. The power is 1 minus a little bit. And actually, I should be slightly more precise and write these phase factors, which these factors of I cancel out if we just have the first power here, so we didn't write them before. Now, in the black hole background, the k squared in the denominator becomes a k squared plus mu squared, and one can argue that at leading order in alpha prime, the string theory answer in the black hole background should be k squared plus mu squared also. So that means that on the black hole background, the growth with s will be a little bit less than s to the first power, even for 0 transverse momentum exchange. So something sort of interesting happens here, which is that in gravity, it was sort of invisible in our calculation, but all of the different Fourier modes in transverse space, all the different k modes, had the same growth exponent. We just had 2 pi over beta. But in string theory, we find out that that was a degeneracy, and that degeneracy gets lifted. So different k modes have slightly different growth exponents. We can define the Lyapunov exponent as the one with the largest value of this growth, which is where k squared would be equal to 0. And then we find the following formula, 2 pi over beta times 1 minus a correction that I'm going to write in the following way. So here we're using lambda as the 't Hooft coupling of the boundary theory. The 't Hooft coupling is related to the bulk string length in ADS units. And it's related in such a way that 1 over the square root of the 't Hooft coupling is proportional to alpha prime. So finite coupling effects in the boundary theory are like studying string theory in the bulk instead of gravity. And at leading order, one finds that the stringy effects tend to decrease the growth exponent a little bit. They decrease the Lyapunov exponent a little bit. Now, I don't actually know how to go to higher order in this computation for a general black hole, but there's one case that we discussed briefly in the discussion a couple of days ago where this function can be computed for all values of the 't Hooft coupling. And that's the special case where you study this problem for Rindler space in the boundary theory. So Rindler space is a thermal system, but really it's equivalent to the vacuum. And these out-of-time order correlators become vacuum correlators in what's called the Regge limit in the conformal field theory. In the Regge limit, the behavior of the 4-point functions is determined by a quantity called the Regge intercept. And that thing has been computed as a function of the 't Hooft coupling. And if we translate that back to the Lyapunov exponent, then what that gives for this special case, so here's the 't Hooft coupling, here's the value 2 pi over beta, it gives a function that looks like this. It goes between 0 at weak coupling and 2 pi over beta at strong coupling. 1 second. We don't know how to calculate this quantity for the more generic thermal case of the n equals 4 super Yang-Mills theory, or for really very many examples at all beyond this example and the SYK model. But we expect a sort of qualitatively similar curve. And at least the weak coupling computation that we did a couple of days ago, yesterday, and this behavior at strong coupling are sort of consistent with that. You can see the exponent is 0 plus a little bit at weak coupling, and 2 pi over beta minus a little bit at strong coupling. Yeah?
What's your intuition for the form of the slowdown of the string spreading?
The slowdown of what, sorry?
The slowdown of the Lyapunov growth with the string effects?
Well, do you mean in the bulk or the boundary?
The bulk. It's not a trick question.
I don't have a good intuition for that. Like why it decreased instead of increased a little bit from the bulk. It's
And the power that it did and stuff like that.
yeah. I don't have a good intuition for that. If somebody from the audience wants to comment on it, though, I'd be.
But it cannot increase because of bulk causality. Sure.
Yeah, that's a good point. So Juan pointed out that if the exponent was bigger than the scattering that we have in gravity, then we'd be able to violate causality in scattering. And yeah, that fact was actually the inspiration for an argument that we're going to make in a moment, that this exponent can't be bigger than 2 pi over beta.
The naively higher spin fields will grow faster, at least in quantum field theory.
Yeah, and so this type of argument, this type of causality argument would tell you that you shouldn't consider a bulk theory with a finite number of higher spin fields, because then the scattering will be determined by the highest spin one, and then you'll violate causality. String theory is a theory with an infinite number of higher spin fields, and it manages to avoid this because the infinite sum grows slower than pretty much any term. There was another question, I think. Yeah.
Can you just remind us how this compares to if the standard fact in string theory that actually high energy amplitudes are exponentially suppressed because you produce all this stuff?
Yeah. That's at fixed angle. And that's not in the Regge kinematics, but it's connected to this. And it's connected to it through the fact that if k squared is large, then this thing is decreasing. And the fixed angle is sort of connected to the Regge limit through large k squared, where this power becomes less than 1 and it's actually decreasing rapidly. But those kinematics are not relevant for this problem. Okay. So now I'm going to sketch a sort of simplified version of an argument that the exponent can never be bigger than 2 pi over beta. And the argument is based on considering the analytic properties and of a out-of-time order correlator that's closely related to the ones we've been studying, but it's slightly different. And it's called f of t. It's defined in the following way. So y here is the fourth root of the thermal density matrix. So we've split the thermal density matrix into 4 factors, and we've interspersed them with these operators v and w out of time order. So if we calculate this function in gravity, we can use the same machinery that we described. The wave functions will be a little bit different because these operators are inserted at Euclidean locations. Then we find in gravity that this is equal to fd, which I'll define in a second, minus g Newton times e to the 2 pi over beta times t. I'm going to leave off the space dependence. We can consider the space dependence fixed of these operators for the entire argument. Okay, what is fd? fd is the disconnected answer for f. It's just the product of the 2-point functions of the w operators times the 2-point function of the v operators. So that's what you would get in an infinite n theory, or a 0 G Newton theory, where there's no correlation between these guys. We just get the product of the 2-point functions. And here we find a small correction to that that comes with a minus sign, and that's exponentially growing. So what it would mean to prove a bound on this is that you would like to argue that the correction to the disconnected answer can't be growing faster than e to the 2 pi over beta times t. So the argument for that is based on some properties of this function f. So first, one property is that if w and v are Hermitian, then it's easy to show that f of t is real for real t. But we can consider f of t in the complex time plane. So we can look at f of t plus I tau. And that's going to be given by the following expression. Okay, where these factors that were formerly the fourth root of the density matrix now have powers that depend on tau. And the real part here, t, is just the argument of the operator w, just the time of the operator w. So this function is going to be analytic in a strip of the complex time plane. The boundaries of the strip are where one or the other of these quantities becomes equal to 0. Beyond that point, we'll have times h, times the Hamiltonian. Beyond that point, we'll have e to a positive number times the Hamiltonian, which is not a well-defined operator. So we have analyticity of this function in a strip in the complex plane. The strip has width beta over 2, and it runs between the imaginary part of tau, imaginary part of time being plus I beta over 4 and down to minus I beta over 4. So here's the time plane, t plus I tau. And we have a strip of analyticity where this is I beta over 4 and minus I beta over 4. And we're analytic in the interior of the strip. So actually, Tom Faulkner described exactly the same kind of analyticity of a modular flowed correlator in his talk. And it was analytic in a strip for precisely the same reason. OK, now if we look at this function at the boundaries of the strip, so let's look at f of t plus I beta over 4. Then we'll get the following expression, trace of y squared w of t v, y squared w of t v. And we can think about this trace as an inner product between two vectors, where the vectors are, for example, y times w of t v times y. That's one of the vectors. And the other one is the same thing with the operators in the other order. This is an inner product between these two vectors. And the norm of that thing, absolute value, will be less than or equal to the product of the norms of those vectors, which is equal to the following. So the only difference between these is that y and v are in the opposite order. So this was an out-of-time order correlator, but this one is essentially time-ordered in the sense that the v operators at time 0 are close to each other, and the w operators at time t are also close to each other through the trace.
They're all Hermitian?
Yeah, we're assuming w and v are Hermitian. And this type of correlator is essentially a two-point function. A two-point function between, between these pair of w operators and the pair of v operators at early time. And based on the intuition we've developed for two-point functions, we expect that thing to factorize after the system thermalizes. So this expression should factorize into a product of one-point functions. And those one-point functions, in this context, are actually products of two-point functions of the w's, because we're considering two of the w's to be one of the two operators. Anyhow, based on that argument, one expects that for reasonably large times, this expression should approximately factorize and should be given by the disconnected answer plus a small correction. For the general thermal case, this is an assumption that's being made, that for reasonably large times, we'll have this factorization. That's an assumption. But for the application of the chaos bound to conformal field theories, that assumption can be proven using the OBE. Sorry, to the application to conformal field theories in Rindler space, it can be proven using the OBE. OK, but so now the way this works is here's our strip where the function is analytic. We pick some time after which this statement is true. And then we bound the function on the edges of the strip. This one I'm not going to discuss, but it's easy to argue that the function f should be, we can find a time such that this function approximately factorizes, and the function here is close to the disconnected answer. And then we just use this inequality on the edges of the strip to conclude that the absolute value of f should be bounded by this expression everywhere on the boundaries of the strip. It's also easy to argue that the function is bounded in the strip by something. And it follows that f should be bounded by this quantity everywhere in the interior of the strip. That's a simple argument in complex analysis. Well, there's a fancy name for it, like the Fragment-Lindelof principle or something. But that's a simple result to establish in complex analysis. It's basically the maximum modulus principle for strips. Okay, so now we can complete the argument. Let's imagine that we have some candidate expression for this function, f of t, that violates, well, let's not say that it violates anything. Let's just write a candidate expression. And let's consider the behavior of this function in the strip. So t plus I tau. Here we'll have e to the I lambda L tau. And this correction here is exponentially growing. So if we can arrange that the real part of this expression is positive, then the function f will be significantly bigger than the disconnected answer. And that will violate the thing that we established, that it has to be bounded by fd plus epsilon everywhere in the strip. So we need to check that the real part of this expression never becomes positive. So the real part of this is is proportional to minus cosine of lambda L times tau. And we need it to be the case that the cosine never becomes negative for tau in the strip. So that means that lambda L times the maximum value of tau, which is beta over 4, should be less than or equal to the point where the cosine becomes negative, which is pi over 2. And that implies that lambda L is less than or equal to 2 pi over beta. Now, you can give a more general version of this argument that doesn't involve making this exponential ansatz. And again, that uses some complex analysis thing, the Schwarz-Pick theorem, to demonstrate that the derivative of this function divided by itself can't be bigger than this quantity, without assuming that it's necessarily exponential. Yeah?
If you have a more general out-of-time ordered correlator, do you need to analyze the function in a slab, a multidimensional complex slab or something?
Yeah, so the question is about whether you can apply a similar type of argument to functions that are not f of t, but where we have a more general arrangement of the w and v operators. And actually, it sort of seems not to work. And we don't, based on gravity, it's sort of obvious that all of these things behave the same way. And that seems like a reasonable expectation for many physical systems. But technically speaking, the argument for the bound breaks if you don't consider this particular arrangement of the operators. Yeah, what I mean by this particular arrangement of the operators is the following. For any configuration here, for any complex argument of tau, for any value of tau, if we think about the positions of these operators on the Euclidean circle, then the w pairs are always opposite to each other, and the v pairs are always opposite to each other, but they can have some relative angle that's described by tau. And that is important in this Cauchy-Schwarz statement. Okay, yes?
Why not assume that the Lyapunov exponent is allowed in bands, not just the connected to zero part, but since
That it's allowed in bands? Sorry, could you repeat the
Since
question?
the cosine is periodic, why not assume that there are bands in which the Lyapunov exponent can take values? Why only restrict to the first band?
Oh, because, well, let's suppose that the Lyapunov exponent, yeah, so the question you're asking is the following. If we were just trying to use boundedness at the edge of the strip, then because the cosine is periodic, then there will be a whole bunch of different values, sort of half of the values of lambda, where the real part of this function would be, real part here would be negative at the edges of the strip. But that's not the argument. We used boundedness at the edges of the strip, together with this Fragment-Lindelof principle, like the maximum modulus principle, to argue that the absolute value of the function is bounded everywhere in the interior of the strip by f of d. And if you have one of these values like you're describing, like lambda L was like an integer multiple of this or something, then at some intermediate period, the real part would go negative, and we would violate the bound.
So you're saying you would have to be continuously connected to reach.
Well, no, we can continuously connect it just by varying tau, by studying the function for different values of tau. And if lambda had one of the large values you're describing, then we would violate the bound at some intermediate point. Yeah, one more question about this, and then I want to move on. Yes?
Is the factorization corrected by 1 over n effects? Or?
Yeah, the factorization is corrected by 1 over n squared effects. And the important point is that the factorization of this function here with the operators ordered in that way, the correction to factorization is not expected to be growing in time. So it's a 1 over n squared effect that's not growing in time, whereas this one is growing in time. And that's an assumption in general, but it can be demonstrated for the case of the conformal field theory Rindler space. Okay, so far in these lectures, we've been talking pretty much exclusively about these two things, which you're probably very bored of by now. The decay of the two-point functions, which is supposed to be a probe of thermalization, is inspired by these Ruel resonances in classical physics, and the growth of these double commutators, so the decay of these out-of-time order correlators, and that's sort of related, at least in some sense, to the Lyapunov exponents, sensitivity to initial conditions in classical chaos. But there's actually a huge literature on quantum chaos which goes back decades and focuses on another aspect which is really interesting, which is something which doesn't have a good classical analog. So it's a sort of uniquely quantum mechanical aspect of chaos. And this has to do with the spectrum of energy eigenvalues. And that's what we're going to spend the last 45 minutes discussing. So in the lecture yesterday, Juan drew a plot of the density of eigenvalues for the SYK model. He drew some kind of smooth curve that looked like this. Let's imagine that we have some quantum mechanical system, and we look at the density of eigenvalues, and then we zoom in on some particular region. We zoom in there. When we zoom in closely enough, we'll resolve this smooth density into a bunch of delta function spikes corresponding to the individual energy levels. And we can imagine trying to understand the statistics of these energy levels. And your first guess might be that they should be some kind of random numbers. And a reasonable definition of a random number would be what's called Poisson statistics, where you take the interval and then you just throw darts at it. You would assign the energy levels to be independently, uniformly distributed random numbers in that interval. So I want to try to draw something like a sample of what that would look like. I'll draw the different energy levels as the vertical location of these lines. a typical sample of something Poisson distributed might look like this. With a fair degree of bunching and a fairly irregular spacing between the energy levels. So this is what you get if you just throw darts. This is called Poisson distributed. And an empirical fact, which goes back to thinking about nuclear spectra and quantum mechanical versions of billiards problems, like the thing that we discussed in the first lecture, up through discussions, let's say, of chaotic spin chains, and many body systems like the SYK model, is that the statistics of the energy eigenvalues for chaotic theories don't look like this. They don't look like this at all.
I think you mean the differences of Poisson distributed. The eigenvalues are uniformly distributed.
Yeah, the different eigenvalues are uniformly distributed, and that's referred to as the Poisson statistics. So this type of distribution, where the eigenvalues are distributed by throwing darts at the interval, is referred to as Poisson statistics.
But the thing that will follow the Poisson distribution is the differences.
And that's the reason why it's called the Poisson distributed. So the empirical observation is that the statistics of the energy eigenvalues doesn't look like this. And instead, I'm just going to try to draw for you. Oh, sorry. One technical point, which is confusing if you try to check this yourself, is that the statement is only about the energy eigenvalues within a given symmetry irreducible block of the Hamiltonian. So often in Hamiltonian systems, we have some symmetries. Like if we have a spin chain, translation invariant spin chain with periodic boundary conditions, we'll have a translation symmetry. The following statement is only true in a given symmetry irreducible block of the Hamiltonian. So you have to do all of the trivial symmetry diagonalization first, and then look at a given block and look at the statistics of energy eigenvalues within that block. And the type of thing that you would find would be some distribution which looks a little bit like this, where in particular the distribution of levels is much more uniform, and you don't have this clumping. By the way, one argument that in at least some integrable theories you have this type of statistics is if you have a free theory, then the total energy is equal to a sum of a bunch of eigenvalues of the commuting terms that make up the free Hamiltonian. And under mild assumptions, if you add up a whole bunch of numbers, then the sum of those numbers will be uniformly distributed, and you'll find Poisson statistics. But that isn't true for chaotic theories. Anyhow, the observation that was made about this is that the statistics of the energy levels that you find closely resembles the statistics of energy eigenvalues of a random matrix. And it depends only on very basic properties of the system, like time reversal properties of the system. And you use the appropriate random matrix class with those time reversal properties. And then you find a good match to the statistics of energy eigenvalues that you find. This is an extremely universal conjecture. It's supposed to apply to almost any kind of interacting quantum system. So it's it's an extremely universal conjecture. And it's based largely on empirical observations, like numerical diagonalization of these billiards problems or spin chains and so on. But in the last 10 years or so, there's been some really interesting progress on this, which is based on an earlier approach of Berry and Gutzwiller and Sieber and Richter and others to study a classical system that you've quantized. So like one of these billiards problems. Then it's been shown that aspects of the random matrix statistics of the eigenvalues follow from a formula, a sort of formal expression for the quantum density of states in terms of a sum over the classical periodic orbits. You then use universal properties of long periodic orbits in classical systems and conclude that you have random matrix statistics in an appropriate sense for the quantum energy eigenvalues. And this is a really nice result. It establishes a connection between classical chaos and this sort of intrinsically quantum mechanical property, the distribution of energy eigenvalues. So I'm going to discuss briefly one aspect, sort of the first non-trivial aspect of the distribution of energy eigenvalues for a random matrix. And then I'm going to sketch, again, the sort of first non-trivial part of the derivation of this result involving periodic orbits for a particularly simple special case. Yeah, there's a question?
So just to clarify, the randomness here is because you scan the different, you zoom into different regions, or you consider randomness system?
Either, yeah, that's a good point. So the question is, when you say that they look like they're drawn from some ensemble, what does that really mean? If we have a given Hamiltonian, we just have a set of numbers. But we can get statistics by taking the window we're looking at and moving it along the spectrum. Or for certain classes of theories, we can vary some disordered parameters in the Hamiltonian, like for example in SYK. You could take that approach, and then you get statistics for the energy eigenvalues. Either of those work, yeah. Yes?
How do we expose this aspect of the spectrum in quantities that we know and care about?
I'll discuss that in a moment. The question was, how do you see these, how do you expose this aspect of the statistics? And I'm going to discuss that in a moment. Any other questions? Okay, so let's start. So I'm going to start by discussing briefly an aspect of the statistics of eigenvalues of a random matrix. And we'll talk about the most famous ensemble of random matrices. It's called the GUE ensemble, or Gaussian unitary ensemble. And it's an ensemble of L by L Hermitian matrices. So we'll let H be an L by L Hermitian matrix. The ensemble is defined by a probability distribution on these matrices, which is the following. A Hermitian matrix has n squared independent components corresponding to the real and imaginary parts of off-diagonal terms and just the real parts of the diagonal terms. And we take a distribution on those components that's determined by the function e to the minus L over 2 trace h squared. So this thing is really just the sum of the squares of those independent components. So the different components are independent and Gaussian distributed. Take a matrix and you fill it up with independent Gaussian distributed components. And if you ensure that it's Hermitian, then that's the GUE ensemble. Now, we'd like to analyze properties of the eigenvalues of these matrices. We're not interested so much in the matrices themselves. We're interested in the eigenvalues. So it's convenient to process this probability distribution for the matrix elements into a distribution for the eigenvalues. One way to think about that is to think about unitary conjugations of the matrix as a gauge symmetry. And then we're interested in gauge invariant information, which is the spectrum of the matrices. And the probability distribution for the spectrum can be obtained, if you like, by a Faddeev-Popov determinant procedure, but it's maybe the most trivial Faddeev-Popov determinant computation. And what one gets for the eigenvalues is a distribution, well, part of it's easy to guess. We just have this distribution translated into the eigenvalues themselves. So the sum over A here is implicit. We have this is equal to the trace of the matrix squared. And then we have a factor that arises from the determinant, which is a product over distinct pairs of eigenvalues. Lambda A minus lambda B squared, where we only run over A less than B in the product. This expression here is called the Vandermonde determinant, or the square of the Vandermonde determinant. I forget what the right terminology is. So this is the distribution for the set of eigenvalues in the GUE ensemble. And you can sort of see already one aspect of this, what we saw here, which is that the distribution vanishes when the eigenvalues are close to each other. When a pair approach each other, it vanishes quadratically because of the Vandermonde determinant. And this is a phenomenon that's known as level repulsion. And it's one of the easiest things to check numerically if you have a bunch of eigenvalues, to check whether it looks like this distribution or that distribution. You compute the probability distribution for the spacing between adjacent pairs. And in GUE, you find that that distribution vanishes quadratically as the eigenvalues approach each other because of this factor. Now, this is a very interesting distribution, especially at large L, and it has a number of really cool mathematical properties that make it possible to analyze marginal probability distributions for subsets of the eigenvalues and many things. I don't have too much time to talk about the nice techniques for analyzing this, but I'm going to put references in the online references for the lectures, in particular to some really nice notes online on Terry Tao's blog. But we're going to sort of compute the first, the first non-trivial aspect of the, well, in some sense, the first non-trivial aspect of the statistics of these eigenvalues. And we'll do that in a sort of heuristic way. Yeah, what's the question?
Is there a gap as a function of L?
Is there a what?
Is there a gap in the 0th eigenvalue and the first one?
Yeah. So the probability distribution for any pair of eigenvalues being equal is 0. So it's measure 0 that eigenvalues coincide. So the eigenvalues will all be distinct. And in particular, the lowest energy eigenvalue will be separated by some distance from the first.
Which grows as L grows.
No, the typical gaps are very small, and we'll get to that in a second. Okay, so the sort of heuristic method that we're going to use is based on a rewriting. Yeah, I can write the first thing here. A rewriting of the probability distribution for the eigenvalues in terms of a density function. So we define rho of lambda to be 1 over L times the sum of eigenvalues of a sum of delta functions at the locations of the individual eigenvalues. So we would like to recast the probability distribution in terms of a functional of the density of eigenvalues. And then we'll analyze that by sort of conventional methods. Okay, so we can just write that probability distribution for the eigenvalues in terms of density rho of lambda as follows. So let's first write the minus L over 2 lambda a squared term. That it becomes minus L squared over 2 times the integral d lambda rho of lambda times lambda squared. This L squared overcancels the 1 over L, and we get a factor of L. And then the integral picks up the values where the delta function clicks, and we get the sum of the squares of the eigenvalues. Then we should write the Vandermonde term, and that's it's again L squared, because we have a double sum, so now we need to cancel 2 factors of 1 over L times a double integral. Okay. So now the reason why this is a heuristic derivation, and I don't know if there's a really systematic version of this, The reason it's a little bit heuristic is because the measure that we're supposed to integrate over in the probability distribution is over functions that are sums of delta functions. It's really, the measure is over eigenvalues. But we're going to ignore that and pretend that we were supposed to integrate over smooth functions, rho of lambda. And there's a sense in which a smooth approximation to the eigenvalue distribution should be accurate for some purposes. If L is large and we have many eigenvalues, and we're going to proceed with that sort of heuristic assumption. Okay, but it's a this is a totally standard technique in the discussion of large L properties of random matrices. So one thing you can do is notice that for large L, we have a large parameter multiplying the entire action. So as Juan described yesterday for the G and sigma action in SYK, we can analyze it for large L by just solving the classical equations, solving for the saddle point in this variable rho of lambda. And this is a very standard computation, which I'm not going to go through, but you find the saddle point is what's called the semicircle distribution, which I'm sure many of you have heard of or derived yourselves. It looks like this. So this is a unit normalized distribution from -2 to 2. The actual density of eigenvalues would be this thing times L. And L we should think of as a very large number. So we're fitting a very large number of eigenvalues into a small region of size 4. So that means that the eigenvalues have to be very closely spaced. Their typical spacing will be proportional to 1 over L. So that's the answer to a question that was asked previously. Okay, but we're actually not so interested in this semicircle. The thing we're interested in are small corrections to that. Small corrections that come from expanding about the saddle point. By the way, this is also something that one is interested in discussion of the SYK model. You study not just the classical solution for G and sigma, but you study also the fluctuations about that saddle point. And this is, well, it happens all the time in any saddle point analysis of an integral. So what we do is we write rho of lambda is equal to rho semicircle of lambda, that's the saddle point, plus a small correction, delta rho of lambda. And then we look at the action for this fluctuation, delta rho of lambda. That's easy to work out. The linear variation will vanish, and the action for delta rho will just come from this second term, this quadratic term. So we find a distribution for delta rho that's proportional to exponential of minus L squared, well, we start out with plus L squared times this expression here. That's a little bit unpleasant because it's a bilocal expression. And it's convenient to rewrite delta rho in terms of a Fourier transform. Delta rho of S is equal to integral d lambda e to the lambda S. Delta rho of lambda. So we use a Fourier transform. And then we can write that term there as equal to minus, there's some number here that I forget, times the integral ds, delta rho of S, delta rho of minus S, divided by the absolute value of S. Here we're using the Fourier transform of the log of absolute value of x is equal to 1 over the absolute value of x plus a delta function term. The delta function term doesn't contribute because we should study fluctuations that preserve the normalization of the spectrum, so they don't have a zero frequency component. Okay. So this is the quadratic action, or small fluctuations about the saddle point. And we can use that to compute the correlation function, let's say the 2-point function of these fluctuations. That's easy to do in momentum space. We just invert this propagator. So the 2-point function in momentum space looks like it's proportional to the absolute value of s. And then we Fourier transform that expression to go back to position space, or eigenvalue space, and we find the 2-point function in this ensemble, delta rho of lambda prime, is proportional to, there's a minus sign from the Fourier transform of s, 1 over L squared, and then the Fourier transform itself is 1 over lambda minus lambda prime squared. So this is the Fourier transform of the absolute value of s. Okay, so we find a power law correlation between these eigenvalues. So that's a correlation that's surprisingly large at long distances between the eigenvalues, and it's a power law anti-correlation. So if you have some extra density here, you're likely to have a negative fluctuation somewhere else, and the correlation is only decaying like a power of the distance. This expression breaks down for small distances between the eigenvalues. In particular, for distances that are close to the typical eigenvalue spacing, you have to use a more accurate formula. Unfortunately, I don't have time to derive that formula. It's a famous formula called the Dyson's sine kernel. And at large distances, when you're considering the correlator for eigenvalue separations that are many times the basic spacing between eigenvalues, then this is an accurate approximation. So that justifies this sort of heuristic derivation. One point about what this means is it's sometimes referred to as diagnosing the rigidity in the spectrum of the matrix, which means that fluctuations in the density on reasonably large scales, which correspond to smooth functions with small values of the Fourier variable s, are strongly suppressed because this factor becomes large when s is small. And that strong suppression leads to this power law anti-correlation between the eigenvalues. Okay, so there's a huge amount more to say about the statistics of eigenvalues of random matrices, but we're going to stop there. It's sort of the first non-trivial result because it is the first thing that's easy to see in the perturbative expansion about the saddle point, about this semicircle saddle point. So if you already knew about the semicircle, then this is sort of the next thing that you should understand, the small fluctuations about it. So now we're going to turn to a version of the derivation which has been given that exhibits this, this anti-correlation of eigenvalue density. This is one of the things that people have been able to establish for semi-classical quantum mechanical systems. Yeah?
Are the corrections to the semicircle bounded below, like does the spectrum technically have a tail?
Yeah, that's right. The spectrum has a tail, and for very large, that's actually an interesting subject all by itself.
Go into problems with the fact that you use like analyticity and some strict, like you use the boundedness of the spectrum to make those statements, or like bounded below. When you have the like tau base, like the h appearing in the exponential.
Well, that's for a, yeah, that's for a quantum mechanical Hamiltonian, a particular Hamiltonian where it will be bounded below.
But here it seems like you have like technically tails on the spectrum.
For a given Hamiltonian, there will be some ground state. What happens in the distribution is there are extremely unlikely Hamiltonians that have eigenvalues with very negative values, and those occur very rarely. But yeah, so the question is about an interesting subject in its own right, which is corrections to the semicircle. And this is actually a complicated subject. And I believe the way it works is that for very large, the distribution of eigenvalues is actually supported everywhere. And for very large values of the eigenvalue, it's suppressed in a Gaussian, e to the minus L times lambda squared. Gaussian suppression at very large values of the eigenvalue. And at an intermediate range, which matches onto the semicircle, there's a Airy function behavior. And this is quite an interesting subject that we're not going to be able to discuss. Okay, so as I was saying, the quantum chaos community has managed to reproduce basically this feature for semi-classical quantum mechanical systems, like, for example, this billiards problem that we discussed. So a particle moving around in some kind of chaotic billiards. We drew this one. But something that Juan mentioned in his lecture yesterday is that there's a sort of a simpler version of a chaotic billiards problem, which is just to consider free particle motion on the hyperbolic plane. So we can consider the hyperbolic disk here. And if we consider geodesics, then although it's not obvious from this drawing because it blows up, because the metric is large here, these trajectories are diverging from each other exponentially. So motion on the hyperbolic plane is an example of a theory where you have exponential divergence of trajectories. In order to get a quantum mechanical system with a discrete spectrum, it's convenient to consider not the full hyperbolic disk itself, but a quotient of the hyperbolic disk by some subgroup of its symmetry group, SL2R. So there's a huge interesting family of discrete subgroups of SL2R, and we pick one of those subgroups and consider the quotient of the hyperbolic space by that group. And depending on the subgroup, we can get a finite manifold. So, for example, a way to think about the type of thing we can get is a fundamental region for that identification might look something like this, where different sides of this guy are identified in some way. So this would be a fundamental region for a hyperbolic quotient. They have, you can consider hyperbolic quotients with large volume. Those have large genus. And again, the motion of geodesics on this space is unstable. They deviate from each other exponentially. But in this space, we have non-trivial closed paths. So for example, a closed path could be this one here that goes out there. It comes in over here after using the identification. And this would be an example of a closed path on this hyperbolic quotient. And we can have closed geodesics. And those are going to be important in the discussion that follows. So there's a formula called the Selberg trace formula that gives an expression for, essentially an expression for the density of states of the Schrodinger operator on this space in terms of a sum over the the periodic geodesics. Now, before I introduce the Selberg trace formula, let me mention a simpler problem that will hopefully clarify its meaning. So let's imagine that we have a particle moving on a circle of length L, and we're interested in computing trace of e to the beta times the Schrodinger operator, the Laplacian, on that space. The eigenvalues of the Laplacian are minus n times 2 pi over L squared. So this expression will be equal to a sum over the spectrum e to the minus, let me put up 1/2 here, beta over 2 times n times 2 pi over L squared. Now, we can rewrite this expression using the Poisson resummation formula as a sum over the Fourier transform of this Gaussian, which is again a Gaussian. And we find a formula that looks like this. sorry, n, this is an n. Okay, and this expression here can be understood as follows. We consider a formula for this trace, which is just the Feynman path integral, an integral over paths on this circle, periodic paths, with the action of x dot squared ds. So s is a parameter along the path, and this gives a formula for this trace. Then we can consider paths that might wind around the circle m times. So that would correspond to x of s that's equal to m times L over beta times s plus a small fluctuation, or plus some circularly periodic fluctuation. And if we evaluate the classical action of this guy, then this term here, the action here, x dot squared, gives us this action, and the integral over these fluctuations gives us these prefactors. In particular, there's a zero mode, which gives us this ratio L over the square root of beta. So this is an example where we have a formula that's the sum over the spectrum of this quantum mechanics operator, this Schrodinger operator. And it's given in terms of a sum over periodic orbits on the circle. Sum over periodic orbits with this factor. So the Selberg trace formula is basically that for these hyperbolic quotients. And I'm going to write the formula. The formula is a little bit long, and I'm not going to try to put all the 2 pi's and things in the right place. But the formula can be expressed in the following way. We have z of beta. That would be this thing, but where the Laplacian is a 2-dimensional Laplacian for our hyperbolic quotient. And it's convenient to put a factor of e to the beta over 8 over here. This thing is equal to first term, which is proportional to the volume of the hyperbolic quotient, divided by 2 pi times times the following expression. And then we have a sum over periodic orbits, so periodic classical trajectories on this hyperbolic manifold of, actually the first sum is over what's called principal periodic orbits. In our circle example, that corresponds to an orbit that just goes around the circle once. We'll sum separately over the repetitions of that orbit in a second. But here we consider a sum over the principal orbits, the length over square root of beta times sum over m Okay, so this is the formula, and there's another constant, the numerical constant that multiplies this form, the second term, which I haven't written. Now, the way this formula is traditionally derived is by starting with an expression for the heat kernel on the hyperbolic space. This trace we're interested in is the trace of the heat kernel. The heat kernel is just that operator, e to the beta times the Laplacian. And there's an exact formula for the heat kernel on the hyperbolic space, on the disk. It's a fairly simple formula involving an integral. It's an integral expression for the heat kernel. And you can compute the heat kernel on the quotient just by summing over images. So you have an infinite sum over images that gives you an exact expression for the heat kernel on the quotient. And then you process the sum over images into a sum over these periodic orbits. That part is a little bit complicated, and you have to do some, again, not completely trivial integrals in order to get this expression. But I didn't want to go through that, both because I didn't have time and because this formula actually looks sort of simpler than that derivation suggests. And we can sketch an argument, or at least explain part of this formula in a simpler way. So that's based on considering the sum over the orbits semiclassically. So as an example of a periodic orbit, let's take a very simple quotient of the hyperbolic disk, where we just quotient by a group that's isomorphic to Z, which acts in what's called an elliptic way. So here we have the hyperbolic disk. Let's imagine that we quotient by a group element that has fixed points here and takes this slice to this slice and so on. It acts in that way. So a fundamental region for this, for the identification would be, for example, this region here. This is a non-compact region, but so in practice, in order to get this quotient, we're quotienting by a larger discrete subgroup, but it will include things like this as a subgroup. And we can write a metric for this region as a piece of global ADS2 with an identification. Let's say tau is identified with tau plus L, where L is this length here. So we'll have a non-trivial geodesic in this fundamental region, which looks like the image on the quotient of this geodesic here. And that's something that just sits at rho equals 0, and tau is equal to L S over beta. And if we, over beta, and if we traverse the orbit m times, then it looks like L S over beta times m. Okay. Now, let's imagine that we're following the approach that we sketched above, where we use the Feynman path integral to compute this trace. So we're interested in computing the functional integral over paths. And for this curved space, we should use the hyperbolic metric and consider this operator here. And this functional integral gives us the partition function. So we can consider the contribution to this partition function coming from this geodesic plus small fluctuations about it. So let's write that rho is equal to 0 plus some small fluctuation, delta rho of S, and tau is equal to this expression plus some small fluctuation, delta tau of S. Okay. If you plug these expressions into the quadratic action and use this metric, then you get quadratic expressions for the action for delta rho of S and for delta tau of S. The action for delta tau of S is exactly the action that you got for the case involving this circle. It's the same as the action for delta x of, I should have written delta x of S, but I accidentally wrote delta x of t up there. So it's the same as that action. And the integral over delta tau of S gives us a factor of L over square root of beta, which can be compared to this factor, L over square root of beta there. It gives that for the same reason that we got it in that case. You can understand it as coming from a zero mode in the delta tau integral. Sorry, let me try to finish. I'll discuss questions later. If we consider the integral over delta rho, then its action looks like the action for a harmonic oscillator to quadratic order in rho with a frequency that's given by L times m over beta. That's really trivial to see if you plug this expression into there. I wanted to show you, but I don't even have the like 1 minute it would take. So we have a harmonic oscillator with that frequency, and its partition function is 1 divided by sinh of beta times omega over 2. That's a general formula for the thermal partition function of a harmonic oscillator. And that gives us this factor. The frequency is m times L over beta. M times L over beta divided by 2 beta gives this expression. So this classical plus small fluctuation analysis actually gave us more than it seemed like it had a right to give, which is that it gave the exact expression for the sum over orbits. I might have made a mistake when I was looking at this, but it doesn't seem to give the exact expression for the first line, but I might have done the calculation wrong. But it seems to be an unexplained fact that should be explainable, that the sum of these orbits is 1 loop exact. Anyhow, this is supposed to give some explanation for this formula of understanding where the terms come from. We're summing over these orbits and the fluctuations about them, and they give this sum. Now, something that's a mathematician would not approve of, but that will be useful for us, is to try to do an inverse Laplace transform to this partition function to recover the density of states, rho of E, that gives rise to it. So in other words, we assume that the partition function can be written z of beta equals integral over energy of some density of states of energy with the Boltzmann factor. We assume this. And then we can compute rho v by doing an inverse Laplace transform. And if we do that term by term here, then we get an expression, a formal expression, which looks like this. Rho v equals, putting this in quotes for reasons that you'll see in a second. The first term gives volume, I think it's a 4 pi and tanh pi k. So here we're going to use variables where E is equal to 1/2 times k squared plus 1/4. So this is the first term. And then the other terms give oscillating corrections. Okay, it's easy to verify that expression starting from this formula and this expression. It's a little bit harder to go the other way, but it's true. Now, this expression is put in quotes because it's a divergent sum. The first term here gives a reasonable answer. For large energies, this tanh is approximately 1, and it gives something proportional to the volume, the true volume of our hyperbolic quotient. This sum here is an oscillating sum because this cosine is an oscillating function of k. And it looks like the sum has a good chance to be convergent because of this exponential suppression in the denominator here. But in fact, the sum is divergent. It's exponentially divergent. And a nice way to show that is as follows. We can compute the, sorry, this isn't a sum over L, this is a sum over orbits, which have length L. And the point is that the number of orbits of length L grows very rapidly with L. You can actually get that from this formula here. So the way that works is you take beta to be very large, and the partition function as a sum over the energy eigenvalues will be 1 when beta is very large, because the ground state of this system has 0 energy. It's just a constant function on the hyperbolic quotient. You can then ask, if beta is very large, well, this term is ignorable, and somehow we have to get 1 from this expression here, keeping in mind this e to the beta over 8. And that can only come from the very large L region of this sum. And, well, by assuming that there's some distribution of lengths, you can determine that the distribution of lengths has to be, the number distribution of lengths for large lengths has to be e to the L divided by L. So that e to the L is bigger than the sinh of L over 2. Let's say we're looking at m equals 1, and this series will be divergent. That's actually a good thing, because the density of states is supposed to be a sum of delta functions. And this looks like a smooth function, so it has to be able to be infinite in places to be a sum of delta functions. Okay, now, one point that's, well, that might have some kind of a lesson for thinking about black hole physics is that if we look at the partition function, the formula for the partition function, and we're at reasonably high energies, so that beta is small, then the sum over these orbits gives extremely small corrections to the partition function. So the partition function almost just looks like it follows from this smooth density of states here. But those tiny corrections, e to the minus something over beta corrections, if you sum them up, are enough to restore unitarity in the sense that the density of states of that formula there actually follows from a density of states, consistent with a density of states that is discrete. That's a discrete sum of delta functions. And one signal of that is that when you go to try to compute the density of states, the sum blows up in your face. It was tiny corrections for the partition function, but a divergent series for the density of states. Okay, so I actually, unfortunately, don't have time to tell you about how you derive this repulsive anti-correlation of the eigenvalues, but I don't have time to write a formula, but let me just tell you, it's a very short derivation from this point. The way it works is that you write a product of these density of energy, rho of E times rho of E prime. And you forget the smooth term, you look at the sum over these oscillating terms. And you look at the product of the densities, and you integrate over, let me write one formula. You look at the following quantity, rho of energy plus x over 2 times rho of energy minus x over 2. And you integrate this over energy. So this is a way of actually getting statistics, given that we have a fixed spectrum. We integrate over the sort of center of mass energy, and we look at the dependence on the difference. You plug this expression in here, and you argue that the integral over energy kills basically all of the terms except for the terms where you're summing over the same orbit in the two sums. There's one sum over orbits for this expression, one sum over orbits for this one. You argue that it's only the diagonal terms that contribute after the integral over energy for a large range of energies. You then assess the behavior of that diagonal sum using this approximation for the density of very long orbits. This exponential factor cancels the two sinh in the denominator, and you get an integral that gives 1 over x squared, minus 1 over x squared. So in that way, you derive the formula that we found in random matrix theory. The pair correlation function was proportional to minus 1 over the difference in energies squared. You get that in this way here. So let me just close with the following comment. We understood in the first couple of lectures a many-body quantum mechanical version of these 2- and 4-point functions, and we saw that it was easy to compute them in black holes. Like black hole physics very naturally allowed us to compute these diagnostics of quantum chaos. But if we really think of black holes as quantum chaotic objects, then they should also have this random matrix theory behavior in the spectrum. So we would like to have some understanding of that from the bulk, or well, maybe that's too specialized. a more general statement is that we would like to have an understanding of this random matrix theory behavior for general chaotic systems. If it's such a universal property, then we should try to find some kind of a universal explanation. Okay, so let me stop there. Thank you very much, and I apologize for not taking questions during the end there.